All right, so still in the same section, picking up where we left off. And again, I apologize if there was an overlap in problems. For instance, we're going to talk about piecewise functions today. If you had a piecewise function last night and you had trouble with it, hopefully this will help clear it up. Yeah, so there's my apology. Let's talk about graphs. And again, this should all be review. Should be. But we have a piecewise function. It's called a piecewise function because there's pieces and it's a function. So then when everything is said and done, if it's a function, what must be true about it? Good, it passes the vertical line test. It must still be a function. When people start graphing piecewise functions, they get all fancies in their pantsies, and next thing you know, they've got overlaps and things don't pass the vertical line test. There are a couple different ways that you can graph the piecewise functions. What method you want to use, again, staying with our theme, is whatever works best for you. Okay, and I'll show you a couple different techniques. But like it says in red, you want to be very careful graphing these by emphasizing whether you have an open circle or a solid dot, because that can make the difference between it being a function or not being a function. Okay, so let's graph this puppy. Different ways that people graph piecewise functions. The most common method that I find is people graph the function and then get out the eraser and erase the parts that don't apply and then add a solid dot or an open circle on it. Great. Do all three of them, erase what doesn't belong, boom, you got your piecewise function. Others will graph each individual function, then get out the eraser, move on to the next one. Or some people can just do them as the individual parts. I'm the type that does the last one, so I'm going to use that method to graph this. Okay, so I'm going to start with the easiest, the bottom one, no pun intended. What's a graph of 1 look like? Nope. Straight line. What kind of line? Horizontal line at 1. So I could just draw a horizontal line at 1. However, we're all fairly smart enough that we can figure out that I'm only going to go from the numbers 2 and up. Solid dot or open circle? Solid dot. So I come to 1, 2, put a solid dot, draw my graph. Don't forget the arrowheads. Again, if you do it a different way, if you draw that whole horizontal line and then you erase everything from 2 backwards, I'm okay with that too. Whatever works best for you. Okay, then let's use purple. Let's do the line then, that'll be easier. 2x plus 3 has a y-intercept of 3 and a slope of 2. So I could go up 2 and over 1. The problem is that takes me in a domain I don't want to be. So I'm going to go down 2 and over 1. And I actually made a mistake. What mistake did I make already? Oh. Yeah. Yeah, it should be an open circle because I'm not including 0 there. So do a little bit of erasing. Go back to the purple. How are we doing so far? Good? Beautiful. Now the parabola. We'll use green there. Okay, so it's a standard x squared parabola starting at 0, including 0. So I put a solid dot there. And it ends at 2, not including 2. So 2, 2, 4, open circle. It's going to pass through 1. So I get some, whoops. Well, you get the idea. It's over there somewhere. Like that. Is it still a function? Yeah. Passes the vertical line test. And that's why the open circles and solid dots are so important. If we back up, and let's say I make a mistake, and I had filled this in, now all of a sudden, no longer a function. Looking at that graph, excuse me, what's the domain of that piecewise function? All real numbers, beautiful. Moving from right to left, I don't skip any numbers. Where one part of the piecewise leaves off, the other one picks up. What's the range?
Negative infinity to 4, not including 4.
So we're covering all the values from negative infinity up to 4. I agree. Good. So you got to look at the purple takes care of it up to 3, and then you have to make sure that there's part of the graph between 3 and 4 here to account for it. So the domain was negative infinity to infinity, and the range was negative infinity to 4, whoops, not including 4. Because that should be an open circle. Well done. Any problems with that? Still review, yes? Okay, good. And if not, hopefully this is, if you had forgotten about it, hopefully this is helping you a little bit along the way. All right. Transformations. So as our graphs get more complicated, the way I like to approach it is asking myself a simple question: what's the mother function that I'm starting with? And then, what did I do to that mother function to get this new graph? Okay. And there's pretty much 3 things you can do. You can slide it up, down, left, or right. You can flip it. You can flip it over the x, over the y, over the origin. Or you can scrunch it. Scrunch it, stretch it, one of those things. No, turning's a completely different animal, and we don't want to go there. Yeah, rotations are... No, that's like polar stuff. Okay. Let's get right to the fun. Right there. That graph does a nice job of summing everything up. When you take numbers and you attach them to the graph, it matters where that number lies. So, for instance, if I take something like x squared, okay, so we'll start with the mother function of y equals x squared. And then I add 4 to it. I can add 4 to it 2 different ways. I can just add it on the back end. What's that 4 going to do to the graph? Move it up 4. Beautiful. Or I can put the 4 inside the function. What's that going to do? To the right 4 units, correct. The other problem that comes up is people have a hard time remembering the difference between those two. Does the negative sign outside flip it over the x or over the y? Obviously, with it sitting right in front of us, we realize the answers. But the way I remember it is if I get in a pinch, I go back to a standard parabola. So I take that x squared. Starting with x squared again, I've got 2 options. I either have this or I have that. In other words, the first one, I just put the minus sign in front of it, which is this. The second one, I put it inside the function, which is that. And notice that this just gets me back to x squared. Well, how would I take that parabola and put it back on itself? I would just reflect it over the y-axis. So again, if you're just a memorizer, then just memorize those. If you need some way to remember that or figure it out, there's one possibility. There's lots of other possibilities. Okay. We don't do a ton with graphing, but you should be able to manipulate a graph in the basic sense to figure out where everything belongs and what it's going to look like when you're done, especially when we get to some problems where it'll be advantageous. Instead of grinding out the algebra to solve problems, it's easier to just graph it and take a look at the graph, especially when we deal with things like absolute value. Absolute value is not a good friend of ours in this class. It's difficult to take the derivative of, it's difficult to take the integral of, but if we start drawing graphs of that, we can solve some pretty complicated problems. That's it, we're done. Okay. Questions?